Hey everybody, welcome to another episode of Earthly Headlines. I got some video feed now. I finally figured it out. Pretty cool. So I'm sure it's nice for you guys to match a voice, or match a face to a voice here. So this is what I look like. The lighting might be a little messed up, but you guys can see me, right? Right. Okay, so today's headline comes from Natural History Museum, which has to do with asteroids and how water got on Earth. Now, this isn't new. This isn't cutting edge. A lot of people have talked about how water got here and how the Earth formed and how we got to be called the blue planet. Well, this article kind of goes over what asteroid forensics are and how it could reveal the origin of water. So, up until this point, a lot of talk about asteroid mining and, quote, the final frontier, which is space. It's just been kind of sci-fi-ish. It's just been a lot of talk about like this Trump Space Force and stuff like that. A lot of people didn't see the point or what we would do. The number one thing that people would point to would be asteroid mining. But it doesn't always have to be for profit, such as this case here. We could find out a lot about this history of our solar system, about Earth, about other planets, and about the asteroids that these meteorites come from, and how water came to be on Earth. Because up until this point, I thought I thought it was just literally blocks of ice hitting the Earth, and that's how we got water, was these blocks. But really, that's not quite how it works. So let's go over this article really quick, and let's get to the bottom of this. So first of all, asteroid forensics, that's a cool word that I don't think a lot of people have heard. But basically, if you think about like CSI and how they solve mysteries and stuff like that, they use this thing called forensics, right? They study something and then they go back in its history and they kind of deduce certain conclusions, right? So this article, as we go down, this water did not originate on our planet, and almost all water on Earth was delivered from within asteroids that pelted the young planet after it formed. So this was a hotly debated topic for a while, up until recent history. And they thought water like came underground and it came from the Earth's core or something, or it came from like intersolar or intergalactic. Well, they got closer by saying that it came from intergalactic objects and stuff like that, but now they're pretty sure that it came from meteorites that came from larger asteroids, which had the chemical makeup that included hydrogen and oxygen and the building blocks of water. So this scientist, PhD candidate, I don't think she's a doctor yet. Helena, what's her name? I want to give her some credit. Helena Bates. Okay, so we'll just call her Helena for the sake of ease. And she says so herself. She's doing asteroid forensics. She takes meteorites and then she works out their history, and from there she extrapolates what happened on Earth when they landed, what they're made of, yada yada. So there's just some background. There's a spacecraft called OSIRIS-REx, which is approaching this huge asteroid called Bennu, which happens to be the first NASA mission to sample an asteroid. So right then and there, this is how cutting edge, like we're talking here. This is a world first, right? So who knows what we're gonna find? But there stands to be a lot of implications here regarding how life was seeded here. I mean, if you look at like Yellowstone, those geysers and underwater vents and stuff like that, there's life wherever there's water, basically. And it'll solve a lot of questions about, well, not solve, but it'll answer a lot of questions about whether Mars really had life, because it's pretty evident that there's water on Mars, and perhaps Mars got water the same way Earth did. So there's a lot of questions to be answered from this, and this is going to be a years and years long project. The evolution of other terrestrial planets in the solar system, even origins life itself. Yeah, I just talked about that with Mars, maybe even Venus, Jupiter, etc., etc. Scientists believe the Earth formed about 4.5 billion years ago. That number is debated, but we'll just say the consensus is 4.5 billion years ago Earth started to form. But it was too hot for water to condense, so it was probably just dust. What we know is like dirt, minerals, stuff like that. So the scientists, they concluded that water on the planet came from somewhere else, as well as carbon dioxide, and probably nitrogen, stuff like that, all came from somewhere else. Okay, but where? Right, well, it's probably these flying objects. Look at the solar system. You take the sun, and anything closer to the sun is obviously hotter, right? And anything further away is cooler. So there's this concept that they talk about called the snow line, which is like a boundary. And the further away from the sun, water vapor can condense directly to ice. But the closer it is, it can't do that. It has to go through liquid phase first. But since there's an object outside the boundary called the snow line, it's going straight from vapor to solid. It forgoes that liquid part of the process, from what I understand. So these distant objects, which are the asteroids and quote gas giants and probably meteorites that come from these asteroids, if they were in this position, if they're lucky enough to be in this position, then water, ice as they call it, was available to be created basically in these objects, kind of like I don't want to say like mold on a sandwich, because that's obviously a lot different, but the water was able to form and then hitch a ride on these asteroids and become part of the chemical makeup of these objects. And so they kind of piggybacked on these bodies on these asteroids, and then they kind of come closer to our solar system. They become part of the orbit, and then once the sun reached a more stable state where they wouldn't immediately melt or vaporize as it got closer to the sun, they were able to maintain that orbit. So because of this, scientists are kind of putting two and two together and saying, okay, most of the water on Earth must have been delivered here by these asteroid impacts. And they don't deny the asteroid impacts. These asteroid impacts are pretty much, they happen. It's not really up for debate, although there are people who say that that's kind of it's not feasible. That's BS to me, because look no further than the Tunguska event, right? 1908 Tunguska event, Tunguska event. Look that up, and that's your proof. They have photos of it and everything. It hit some near-Earth object hit Siberia and flattened the whole area. It's crazy. So here's this picture that I like. That's if you were to strip all the water away from Earth and put it and localize it into one spot, it would be roughly half the size of the U.S., not counting Alaska, of continental U.S. I guess Alaska is continental U.S., but take Alaska out. Look at the picture. It looks like it's most of the western part of the U.S. and a little bit of the Midwest. I don't know. Although this is a CGI image, obviously this is kind of conjecture, but if you do the math, that's probably correct. Okay, so to break this down even further, we have to talk about the three main types of meteorites. So there's three types. There's only one type from these three that's the most water rich, which are called the carbonaceous chondrites, which can be up to 28% water. So this is what all the scientists are looking for when they're looking at when they're deciding which meteorites to spend their money on to study, they want to make sure they're picking one that has the molecules that make up water. So, like I said earlier, they're tacked onto the mineral structure. So when the meteorites heat up, such as during an impact with our planet, right? That's a huge kinetic impact that generates a lot of energy. This water gets released as gas, and then the gas. What happens to gas? It kind of goes up, right? It kind of evaporates up, right? But since it's already within the Earth's atmosphere, it gets trapped, and it becomes part of that evaporation cycle. So it evaporates, and then it comes down in the form of rain, and then depending if it was the ice age, and then that rain probably froze in the ice, and then that's how you get ice. That's how you get not retreating glaciers, but built accruing glaciers, bigger glaciers. That's how they advance. That's how they get bigger, basically, if we're in an ice age. Right now, we're not, so the glaciers are receding. Yeah, we're not living in that time period, so it's kind of hard to explain that. Moving on. Her work involves taking the meteorites that have survived their passage through the Earth's atmosphere and matching them up to the asteroids they likely came from. So she's scouring the Earth, the surface of the Earth, to find these, the remnants of these asteroids, and then with the rover with Bennu that NASA is researching, she's gonna do a lot of the legwork and have to really look at both samples and try to mix and match and see what came from where. And then if she's successful in doing that, then we can find all kinds of answers, and we'll get all kinds of data about the history of at least the Bennu asteroid. So how does she do it? So she uses a spectrometer. So the spectrometer shines a range of wavelengths of light onto the rocks, and then she measures what's reflected back, right? She explains it better than I can. When you shine a light on something, bonds in that material absorb some of that light. This means that you see gaps when you look at the reflected light where certain bonds have absorbed a particular wavelength. So whatever is reflected back is not being absorbed. So that can clue you in onto what wavelength the asteroid is absorbing. And if the asteroid she finds, if the remnant of the meteorite she finds on Earth matches, if the same things get reflected back as the ones on Bennu, then more likely than not, they're either that meteorite came from Bennu itself or something like it. That's the best they can do so far. And I'll show you a picture. There's a picture of an example of a carbonaceous chondrite. So that's a really beautiful rock. Look at that. So scientists analyze the light reflected, and they see where the gaps are in those specific wavelengths, and then it suggests that they contain water. And this is a similar technique they use to figure out if Mars had water as well. She compares it to the space telescope data of asteroids in space. So she's not even, obviously she can't fly onto the asteroid herself and dig it up. So she has to go through a bunch of different technology to gather this data. It doesn't mean the data sucks. It just means she has to jump through a lot of hoops, and it's not full. It's not as good data as you would get if you were there yourself, obviously. But this is just to demonstrate all the types of, gatekeepers. Well, I don't want to say gatekeeper, but there's a lot of different filters that she has to go through. So she has that spectrometer, and then she has a space telescope data, and then from there she's going to have to do a lot of legwork and figure out what's what and what belongs to what isn't what, if that makes sense to you. She looks for these same patterns. So there's a lot of attention to detail here, and I can just tell by reading this, it's painstaking work. From asteroid to life, there's another asteroid that the Japanese craft Hayabusa 2, they've already started their observations, and it's called a Ryugu, and their spacecraft is orbiting it. So those are we have two highly reputable scientific organizations that have deployed the necessary technology to extract the data for a further analysis. So that's amazing. I thought we just had one, but according to this article, there's two. So over the next few years, Helena's research will feed into the data that these spacecraft collect, and then from there, we can figure out how the water-rich meteorites on Earth may have originated. And if we could find that out, then we could figure out a more precise age for the solar system, some of the oldest solids and materials of the solar system, what is originally from our solar system and what came into our solar system from a different system. The writer says, objects give us an unprecedented snapshot of what the early solar system was like mere moments after it began to form, including the origin of that all-important water. It lets us peer far back into the beginnings of life. So what are the implications of this? Well, why even bother going through all of this? Our lifespans are so short. We're never going to see the fruits of all this. Why does it matter? Well, who's to say that we are not going to see the fruits of this? This could help us understand the landscape of the solar system much better, or spacescape, whatever you want to call it. It helps us understand more about what we're dealing with when we're talking about interstellar travel, which I think one day we'll probably get there. Who knows, right? I mean, we're talking about it all the time. It seems like humans are drawn toward the outer limits of space, right? But I don't know. That's a different conversation. But there's also technological, there's economic implications. This data could very well change the way we look at how life works in our solar system and how we can better adapt and expand and flourish elsewhere. This could conceivably, although this is kind of rose-colored glasses, but take this with a grain of salt, this could probably end a lot of disputes in terms of natural resources. Because if we can asteroid mine, if we could study and figure out if water did indeed come from these asteroids and where they came from and when, then we can mine other asteroids that aren't as rich in water for other minerals like iron or cobalt, whatever. There's all kinds of lithium. There's all kinds of stuff that we could use and harvest. And if we could harvest from the asteroid belt, or let's say, or whatever near Earth object there is, then it's almost like we have infinite resources. So this is a huge deal, and it's definitely worth putting some resources into to get more information. Because there's only so much information we can get on Earth now. I mean, we can still find a lot of information about our history, like the personal the history of Homo sapiens, which is invaluable as well. But perhaps there's even more. The limits are endless when we're talking about asteroids, stuff that comes and goes in space. That's pretty much it for this asteroid forensics article. I really enjoyed this article. I hope it's okay for me to kind of have this read along with you guys. I thought it was okay. But apparently YouTube might not. But let me know what you guys think in the comments about asteroids. I think this is a super interesting article. Do you think it's worth exploring this further? Let me know. Thanks a lot, guys. I'll see you next time.